Alright, so here we have my current version of an account of exponentiation, as complete as I can make it. There are definitely still things I haven't figured out yet. Probably shit that I will die before anyone figures out. Because turns out to be a lot more complicated than anyone ever told you. Alright, exponentiation of x to the j on u plus I times k. So I is the imaginary component, and this is for all real j, all real u, where j on u is irreducible, so it is a reduced fraction, and all complex x. Right. So it turns out that we don't actually have to care about decomposing x, but we do have to care about decomposing, or the base. We do have to care about decomposing the exponent. All right. Now, if j on u is irrational, then a and v are both 1 on u, and s is the inverse of that. It's just u. Basically, if you get the rational version of j on u, then things are a lot easier. Otherwise, a is j on u, v is u of j on u, and that will be explained in a second, and s is uncountably infinite. Now, the u function, u of n, is the fractional component of n times the fractional component of the inverse of n, which happens to be the same as u of 1 on n, or the inverse of n, right? And the fractional frac n takes only the fractional component of n. This does not yield the unit for an irrational, but for irrationals less than 1, it does guarantee that we have a multiple of the unit for the irrational, which we can work from. Okay, so this doesn't give us the smallest component, which would be infinitesimal. I'm not entirely sure if it's as small as L0, L0. I don't think it is. I think you're going to get holes, but it is still going to be infinitesimal. Starting at 1, right? And importantly, this is not positive 1. This is 1, bare 1 that indicates existence. That 1. At the stage where this exists, the only things that exist are 0 and 1. There is no number line, there is no sign, there is no direction, there are no vectors, there are no fractions. It's literally at this stage where you're starting from, all you have is 0 and 1. And this is important because what exponentiation is, fundamentally, it is, well, so it's an abstraction of multiplication, which is an abstraction of addition, which is an abstraction of iterating, which is incrementation, which is iterated identification of existence. Right. So the bare level is existence. That 1 is important. We have to start at the beginning in order to get exponents to make sense. Okay. Magnitude. To get the magnitude, we multiply by x. We take the 1 and we multiply by x, j on u times. That's it for the magnitude. That's all you do. There's some caveats later on. For the unit, we take s equally distributed solutions, and this is where the a, v, and s come in. And those are just random ass letters that I just use because they look different from each other. They sound different from each other, right? S equally distributed solutions on a complex circle whose radius is the magnitude determined above, right? So if your magnitude turned out to be 1, it would be the complex unit circle. But for the most part, that's not what's going to be what happens. So complex circle whose radius is the magnitude. The first solution will occur at a times the angle of x from 1, right? So if x is complex, then it will have an angle away from 1, and at this stage, so because x is complex, we have now introduced a coordinate system. We have introduced fractions, we have introduced units, we have introduced vectors, and that 1 corresponds in location to positive 1, the positive 1 vector, but it is still distinct. Okay, so now we're getting that a, which is just 1 on u. So basically we're taking the angle away from 1 and we're dividing it by u, if it's rational. Or if it's irrational, we're multiplying by the real component of the exponent. And then solutions occur at intervals of 2 pi times v, which for irrational just means that your angles occur at 2 pi times, or divided by u. But for irrationals, your intervals, they become infinitesimal. This approximation works when you're really well when you're looking at the complex circles, because being irrational, the result of this being irrational, when you put in an irrational, means that it's not going to match up, right? It's not going to, you're not going to land on the same spot ever, twice, right? So as you keep going around, as your angle increases to infinity, you end up putting down a countable infinity of spots, of solutions. The first solution, if the first solution is not on the positive real axis, then there is no solution on the positive real axis. Okay. Alright, now this next part is for the imaginary component of the exponent. The following description of the effect of the imaginary component of the exponent is unsatisfactory as a definition because it is circular. So this is not a definition, it is a description. There is an effect on both the magnitude and unit. So if I were to properly bring this in, it should affect this part and this part separately. But because I don't really even know how to say it, and there's already difficulty saying this, I'm separating it off. Okay? And they are both included together here. And while there are no known errors, some may still exist at this time, I pretty much guarantee you that I fucked this up. Like when I'm looking at this, I'm like, why is this pi and not 2 pi? But that's what I had down, so, and I haven't gone back to look at it. So that could be wrong. It could be right. I honestly don't know. I don't remember. Too much has happened since then. Anyway, each solution is rotated by ln of x times k radians from what the real component of the exponent predicts. As these altered angles grow, magnitudes shrink, yielding equally distributed logarithmic spirals instead of a complex circle. And I'm not entirely sure, I need to play with it, but for irrationals, this should yield, as far as basically just like full logarithmic spirals, but it might also just completely fill the plane. I don't know. I don't really know. So that could be a hell of a mess for irrationals. Magnitudes are inversely scaled by this factor for all integer h, and that yields infinite solutions of all complex powers for any non-zero base, the magnitudes of which range from the infinitesimal to the infinite. So that is, yeah, not a proper definition, because you have exponentiation and logarithms in what I'm saying, so that makes it circular, because we're already requiring the ability to do that in order to explain how to do that. That's not a definition. That doesn't work. Okay. Now here, the starting point of The starting point of exponentiation is always the dimensionless unit 1, which precedes the existence of numbers, fractions, signs, imaginaries, etc., which I mentioned before, and coexists exclusively with the universal reference point 0. It is only by acting upon this 1 that the complex plane comes into existence. And every way in which we get any sort of interaction, even with reals or integers, we have to act upon this, right? In order to get to integers, right, you had to go through natural numbers, the counting numbers, right? And then from there you went to whole numbers, and then you got fractions, and then you got, well, if we subtract a larger number from a smaller number, well, now we get negatives, and now we're able to get integers, and then we're able to get, right, all that. So it builds up, and that building up, you can't ignore it, right? So when you start taking an exponent, you are literally always starting with just the kernel, the bare kernel, the dimensionless unit 1. You are not starting in a world where numbers exist yet. And that's really important. That's critically important to understanding exponents. Like, if all this other shit you forget, that is the thing that should be a takeaway. So if the exponent is 0, the result of the exponentiation is this dimensionless 1. Never positive 1, because positive 1 doesn't exist until after something has been done to the 1 that we started with. And a 0 exponent literally means that we did nothing at all to the 1 that we started with. So if we have a 0 exponent, we do nothing to that kernel of existence. It's not positive. It can't be fractional. It can't be complex. It can't be an octonian. Whatever. It's just the existence. 1. Dimensionless, unsigned, multiplicative identity, 1. Okay? So now here's like looking at this thing, what is happening. And I was just kind of screwing around with, I started playing with a modulo operator, and just kind of took that apart and looked at it and played around with that a little bit. Because basically the goal, if we're working on with, so what I've incorporated here was the irrational real component. The goal there was to figure out how do you actually find at least some of this infinitude of solutions. Right? Because obviously you can't find them all. Unless it's continuous, and I don't think it's continuous. So here, playing with this, as long as our input fraction is less than 1, the denominator on the input is the same as the denominator of the output. It doesn't always give us 1 over, right? But as long as our fraction is below 1, the denominator is the same. And here, if you invert that, right, because u of n is the same as u of 1 over n, right? So if we get something that's larger than 1, we end up with the numerator being the denominator in the solution, because the version of this that is less than 1 would have this larger numerator number in the denominator, and that comes through because of our previous rule. Right? So playing with that, I looked at, the goal of this is to figure out what the unit is, what the denominator is for the irrationals. Right? Unfortunately, we're not going to be able to figure out what the numerator is. But what this does do is it does guarantee us that we get something back with the correct denominator. Right? Something smaller with the correct denominator. So that is helpful. That does lead us somewhere, right? And then you can iteratively take it if you wanted to, and you're just going to go down a path of darkness and rabbit holery. But yeah, I'm playing with like pi and shit here, and you can see like the denominator comes through. If I can select it properly, there we go. Yeah, all those yellow highlighted bits are the denominator, and it came through on all of them. And here we've got, and so here I chose really large prime numbers for the denominator. And then I found, I found what numerator would make that the closest to pi and keep it rational. Right? Or whatever it was. This is probably pi on 4, something like that. Whatever it is. Something related to pi. And then playing with that, I got these confirmed multiples of the unit of pi on 4. So any multiple of pi, or any integer multiple, positive integer multiple of pi, any positive integer itself, pi itself, obviously. So basically this whole top part right here is sort of repetitive, because those first two give you those. But I think the first one I found was actually this one, and this one, the first integers, and obviously pi, And then I actually did have to do a little bit of convincing of myself to that 2 and 1 work, and I may have even done that wrong, so those might be wrong. And then it turns out that if you take pi and subtract off 3, just the 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8, 9, 7, 9, etc., that is a multiple of the unit of pi. So you can just subtract the 3 off, and that's how I know 3 is okay. But then that little thing, you can just take that from pi on 4, or add it to pi on 4, or subtract it from pi on 4, and then you definitely have a multiple of the denominator of pi. Pi on 4 itself also works. 1 minus pi on 4 works. There's pi minus 3. And you can also divide pi on 3 by any positive integer, which definitely guarantees us that the unit for this is infinitesimal. It's incredibly tiny. And so we're never going to find it, and we're never going to be able to use it directly. But we can use these much larger multiples of it usefully, right? So now here it is currently unclear whether there are gaps between the multiples, or if the unit is so small that its multiples yield a continuous range. The unit would then be L naught, which seems unlikely. I don't think that's what's going to happen. However, it is worth noting that if positive I to the 1 on pi yielded the entire complex unit circle, then positive 1 would have to be a solution. This would yield positive I as a solution to positive I to the pi, which seems strange. Either way, the irrational denominator of the proper fractional expressions of both pi and 1 on pi must be an integer multiple of 4, rendering both numerator and denominator rational, the entire fraction reducible, and this all while also being irrational. Alright, so how do you have a reduced fraction where numerator and denominator are both divisible by 4, and if they're both divisible by 4, it's necessarily rational now, but this has to be an irrational number. So there's contradictions in there, and there's enough contradictions in there that I kind of buy it. I'm not a fan of proof by contradiction, because you have to be really sure that your axioms are perfect for proof by contradiction to actually be sound. Not to be valid, because logic is dumb, and you can make whatever stupid axioms you want, and anything that follows from them will be valid. But in order for it to be sound, it has to correlate to reality. So, yeah, your axioms have to be perfect for a proof by contradiction to be sound. So I don't trust proof by contradiction. So I'm not confident enough in this to say that, yeah, that wipes out the possibility, and there's definitely holes. But my strong suspicion is that there will be holes, because there's enough contradictions here that I'm like, yeah, that's probably irreconcilable. Yeah, these appear to be irreconcilable contradictions. So at this time, I suspect that the holes exist. However, irrational exponents may yield full complex circles or continuous logarithmic spirals, or they may have holes. I don't know. So then there's some patterns to keep in mind for the u function. So u of n is u of 1 on n. U of n is also 1 minus n, if n is between half and 1. So for pi on 4, that's actually where this is coming from. U of n is 1 on u if n is between 0 and a half and n is rational. Right? If it's irrational, then the numerator, we can't actually know anything about it. And it's not going to be 1 for sure. It's going to be something fucking crazy. So, yeah, there's that. Yeah, that's about where we're at. So, in order to get irrationals in here for the real component, I kind of had to make this a little bit gnarly, but it does still say the same thing if you This ends up being fairly simple, right? A and V are the same thing. S is just the inverse of it. So, yeah, just kind of plug those in. And to my knowledge, this is the most complete description of exponentiation that has ever existed. I can't find anything that comes close, let alone that is this compact. Even if you just take this part, it already explains more than I've ever been able to find from one source, and it actually explains some things that I've specifically seen people discuss as being known consequences, but they don't know how to so for irrationals, I have seen people say that there must be infinite solutions, but we can only find one of them. Here you can find however many you want. Not all of them. Okay, any amount you want other than all of them. Yeah. So already this does more work than any explanation of exponentiation that you've ever seen, and it is more properly grounded in how the fuck shit actually should work. There are absolutely problems, and there's probably mistakes, but when you have math teachers around the world telling kids that 3 squared is 3 times itself 2 times, which means you take 3, you multiply it by itself, 3, twice, so you get 3 times itself, that's 3 cubed. That's not 3 squared. Okay, right? That's the world we live in right now. That's what teachers are doing right now. So yeah, if you want to whine about, oh, you didn't do this right, or this is too hard to understand, or you're making it more complicated, no, you're wrong. You're wrong.